Hello, P-Statters. I hope you're having a lot of fun. When in doubt, divide by the page number. We are going to be reviewing today so that you can have the opportunity to know what's up for the test. And so our whole plan is to talk about the test format and to review everything that we've done in this chapter. It's fairly straightforward. On the test, you're going to get about 3 pages. Problems that are going to range from fairly straightforward to ones that are a little more challenging. And to review what we've done so far, we began with the concept of vectors as a way of expressing motion. And vectors in physics are objects that have what 2 things?
Speed and direction.
Yeah, or magnitude and direction, exactly. Objects with magnitude and direction. And so fundamentally, we can draw a vector as an arrow, just like that. But then we can go through and with a ruler measure its magnitude and direction. And when we do, what we get is the polar form of that vector, which gives its magnitude and its direction angle. And the advantage of the polar form is that it's easier to read for problems. But we also discovered that what we wanted was a rectangular form. And that rectangular form we can write in terms of AX and AY. And if we look at the arrow for A, then AX is the component that is parallel to the x-axis, and AY is the component that is parallel to the y-axis. And since our direction angle is always measured from due east, then this little triangle, right triangle right here, tells us all the relations that we need to get from rectangular form to polar form or vice versa. So if I need to go from polar to rectangular, then my x component is going to be the...
cosine of it's cosine
magnitude times cosine theta, that's right. And the y component will be exactly so. If I need to go in the other direction, from rectangular to polar, again, the diagram tells the tale. The magnitude of A is found at the Pythagorean theorem. The direction angle was a little bit tricky. You can see that the tangent of the direction angle is always y over x. But when we did the inverse tangent to find that angle, sometimes the inverse tangent would give us the wrong quadrant. Under what circumstances does the inverse tangent give us the wrong quadrant? Well, okay, you do have to watch for radians and degrees. That's a separate thing. But when
angle
yeah, which
Whether or not you're measuring degrees.
I'm measuring right. Assuming I'm measuring from due east, nevertheless, sometimes I'll still get the wrong angle here. Under what circumstances? In quadrant 3 and 2, right? And that happens when what, Lena?
When it's magical.
What? Which is?
Oh,
When the x component is negative. That's exactly it. So that when x is negative, we must manually add 180 degrees to our angle. And a little bit of common sense goes a long way here. If you are looking at a vector that is -2, 4, and I ask you, okay, put that in polar form, Okay, you can find the magnitude, let's call this vector b. Then the magnitude of b is going to be the square root of 2 squared plus 4 squared. How come I don't have to include the minus sign? Negative squared is, negative 2 squared is the same as 2 squared. And that gives me the root of 20, which is another. Two roots 5. Oh, come on, phone. Pay attention. My phone is not paying attention. Pay attention. Okay, guess we'll do this. Everybody else can do root of 20 here. Yeah, it's 2. 4.4. And now when I do the angle, then I do the inverse tangent of y over x, and the inverse tangent gives me, wow, my phone is really not paying attention.
Is it on just the portrait marker?
Nope.
First picture?
There, now it's paying attention. Okay, and so when I do the inverse tangent here, then lo and behold, my calculator says negative 63 degrees. And here's where I want to use a little bit of common sense, because my vector b is clearly over here in quadrant 2. 2 back and 4 up. But the angle that I got was negative 63 degrees, which is down here. That's clearly wrong. And this is the circumstance in which I need to add 180 degrees in order to get the correct angle, so that I get 117 degrees, which is now the right angle. Is everybody following what I'm talking about? And you've done this process, right? I'm just reminding you of things that you know. But I noticed that you weren't very sharp at knowing when you needed to do it. And the answer is we have to add 180 when our x component is less than 0, because that puts us over in quadrants 2 and 3, and the calculator can only give us angles in quadrants 1 and 2. Okay? Now, Alyssa mentioned something that was important. Everybody wants to check their calculator before they get started to make sure it is in degree mode and not radian mode, especially if you're in calculus. All right, what did we use these vectors for? Give me some things that are vector quantities. No. Some things that we measure that come to us in vector form.
Like multiple speeds.
Not
Different directions.
Velocity.
Velocities, right. Velocity is a vector quantity. Speed is its magnitude, right? So we have velocities are vector quantities. What else besides velocities? Position is a vector quantity. What else? Time is not a vector quantity. It doesn't have direction to it. I'm going to go 6 seconds east. That lasted 5 seconds at an angle of 20 degrees. What other things have direction to it? Distance does not. It's the magnitude of your position.
Seems like velocity and position
Covers a lot. There's one thing it definitely does not cover that we have used a whole lot. Acceleration. Does acceleration have a direction to it? Why, yes. Gravity always pulls Ah, not just down, but straight down, exactly. Gravity always pulls straight down. That's a direction. Acceleration. So our big three quantities, velocity, position, and the related displacement, all have direction too. Now, the most frequent type of problem that we worked that involved motion in two directions were the projectile problems. And so as you are practicing for your test, you absolutely want to practice up on projectiles. Projectiles. And in particular, with projectiles, the key point is that as soon as the projectile leaves the hand, gravity takes over, and the motion is uniquely determined by what? Exactly. Motion is uniquely determined by the initial velocity vector, v0, and the acceleration will always be 0, negative g. These are the two things. Now, our basic strategy for dealing with projectile problems was to take that initial velocity and put it into components so that we get v0x and v0y. How do we put it into components?
Convert using rectangular form.
Right? Specifically using what functions?
Put that on
Another way. How do I get, what is the component v0x equal to?
cosine.
It's the cosine component. Now you guys seem mostly quiet here. Does this mean that I'm asking questions and you're going, I don't know? Or does this mean that you're just intently focused? What's that? Okay, good. So you're comfortable with all that. Good. All right. And so our basic plan is to take V0 and then to split up the motion into X and Y separately and use the equations of motion here, having labeled our information one by one. What we found when we solved these projectile problems is that a very common thing that was helpful for us was to find the time. So if you're stuck, consider finding the time, because the time is the one variable that actually transcends these two columns here. What happens in the x stays in the x, what happens in the y stays in the y. But what I can often do is to find something about the y and find the time when that happens, and then find the corresponding motion in the x where that happens also. Does that make sense? So we're thinking of that motion, that projectile motion, as basically happening on film. And when I find the time, when I find the timestamp, that captures the motion in both directions. Okay? In addition to projectile problems, how should you practice these? Here is a strategy tip for you as you practice. I would recommend focusing on a level 1 problem or 2. Make sure that you can do those quickly. Get to the point where you can just whip that out, and then focus on maybe 1 or 2 level 2 problems. Work through those smoothly, not quickly, because you gotta actually think and do some analysis there, and don't touch any of the level 3 problems, because they are more intricate and involved than you're going to find on your test.
So the difficulty will be the same as
Yeah. Yep. In fact, you kind of know already. I'm going to give people a level 1 problem ish type of thing, so that people who basically know what they're doing can get points on that. And then I'm gonna give you a level 2 problem probably that's gonna challenge you somehow in there. That make sense? One of the things that we talked about was range. And remember that range was the delta x when delta y is equal to 0. So we start here, we go to here. Should you memorize the equation for range, or should you be able to derive it? Kind of depends on how much trig you know, right? If you know enough trig, the trig identity, or if you should know the trig identity, then I would say go ahead and practice deriving it for yourself one time, because it's a useful exercise to do that. If your trig is not there yet, because you're still in trig right now, then I would say go ahead and memorize the range equation as a standalone equation. But just make sure that you know what range is talking about. Delta x when delta y is 0. Likewise, sometimes we needed to know something about the velocity up at the top. What do we know about the top of the arc? Velocity in which direction? In the y direction only. And that's important. So the velocity in the y direction only is 0. The velocity in the x direction is a little bit interesting. One more thing to know about projectiles. Since gravity pulls straight down, what's the acceleration in the x direction? What's the acceleration in the x direction? 0. And since the acceleration is 0, that means the velocity is constant. That's exactly right. And you guys that are in Calc 1, now you're starting to see your derivative rules coming into play, right? The derivative of velocity is acceleration. Velocity is constant, so the acceleration is 0. Right. So the velocity in the x direction is constant, that is equals v0x for the entire motion. And one last bit of trivia about projectiles. What is true about the speed right when the projectile lands? Yeah.
It's equal to the initial.
It's equal to the initial speed. That's exactly right. And this becomes important when understanding some things like, why don't you ever shoot a gun up into the air? Answer, because the speed the bullet has when it comes back down is the same that it had when it left the gun. So if you shoot a bullet up into the air and it comes down and hits somebody, it would be like shooting them at point-blank range. Right. So, you know, for some reason, it is a thing sometimes to, quote, celebrate by shooting off guns in the air. No, do not do that. Do not be anywhere near somebody who does that. It is a stupid thing. Okay. The x is constant, v0x for entire motion. I think that covers the projectiles. The only other thing that we did motion in 2-dimension, generally speaking. Projectiles was the most common case of that. The other thing that we talked about was relative velocity. And how do I read the velocity sub AB? What do the A and B refer to? It's pronounced the velocity of A with respect to B, and we call A the velocity of A with respect to B. A is the object whose velocity we are measuring. So we are literally looking at A here and looking at its velocity. But we are measuring it with respect to a reference frame, B. We are measuring the velocity of A with respect to a reference frame B. and B might be an object, or it might just be a point somewhere on the ground. What is our default reference frame if I don't give you a reference frame? The ground. That's exactly right. And so we had two basic rules here. One is that if I measure the velocity of B with respect to A, then the velocity of B with respect to A will be equal but opposite to the velocity of A with respect to B. And that was our first rule for dealing with relative velocity in two different reference frames. In other words, if I am moving forward relative to the ground at 20 meters per second, then the ground is moving backwards relative to me at 20 meters per second. And that's our first-person shooter effect, right? When you are in a first-person shooter game, you push forward, but the way the computer does that is to make the scenery go backwards relative to you. Okay. Then the second rule that we had was that if I add the velocity of A relative to B and the velocity of B relative to C, then what I get is the velocity of A relative to C. And the key to making this work is to make sure that you have object in the second case as the reference frame in the first case. Just like that. Just like that. And so we worked various problems in one dimension and in two dimensions, like that. And I would again focus on level 1 problems, make sure you can do this quickly, and then come back and make sure you can do a couple of level 2 problems smoothly. If you can do all that, you're going to be fine. Let's ask a quick question here, just to make sure you're on. Okay, so this would be a typical kind of question to see if you know what you're doing. How do we proceed? Yeah. Split up into X and Y, good. What do I have in the X, what do I have in the Y?
For the X, we have velocity is 2. Oh, 1, sorry.
Yep.
And then acceleration is negative.
Yep. And in the Y?
Velocity is 2. And acceleration is 4.
Yep. Good. And what other piece of information is true for both columns?
T equals 3.
Exactly. And now we're trying to find what quantity?
Delta X.
Delta X over here, and delta Y over here. Good. All right, what equation should I use?
Delta X equals B0 T plus 1.
You got it. Can you do it in your head?
1, 3 plus
3 plus negative 1 times 3 squared. So negative 9.
3 minus 9 is 6. Negative 6.
Negative 6, that's exactly it. Over here.
6 times 2 24.
Exactly. Good. Just pushing that mental arithmetic on board. Any questions? Yes.
So then, if it's displacement, would you want it in polar form?
I would prefer rectangular. I would just say that
Yeah.
the displacement of the object is that.
But when you say delta x, it also accounts for delta y.
Yeah, you can use.
I know like displacement, it says delta x, but,
One thing I like about our AP Physics book is it uses R for the vector position.
okay.
So if you
Yeah.
want to do that, that helps.
Alright.
I'll see you guys tomorrow. You've been working hard. Come show me what you know tomorrow.
You want?